Hello, everyone. My name is Mark Krumholz, and I'm here because I have been asked to give a brief overview of the earliest phases of low-mass star formation in order to begin this session on planets and planet formation. Now, let me start by saying that this is an intrinsically ridiculous request. I'm supposed to review all of low-mass star formation in 20 minutes. This is patently impossible. I literally wrote an entire book on the topic of star formation. I cannot summarize it in 20 minutes. So what I'm instead going to do is summarize it in 10 minutes. I'm going to spend the first half of this presentation on a pedagogic introduction that is mostly aimed at students and on those who are new to the field. And then I'm going to spend the second half to introduce two recent topics from star formation that maybe haven't percolated to the planet formation and disk communities, but are potentially interesting to you. Now, this is based on what I think you'll find interesting, not necessarily what you will find interesting. So, caveat auditor, hopefully this is something that you will find interesting. So here's the outline of what I'm going to do. I'm going to start with a 10-minute, very brief overview of star formation and how it works. I'll review the galactic context of star formation, collapse and fragmentation, and then disk formation and evolution. And then I'll go on to my two topics of interest to disk and planet people. One is how does stellar clustering affect early disk evolution? What do we know about stellar clustering more generally? And the second is going to be the source of short-lived radioisotopes and what do they tell us about planet formation in general and the solar system in particular. That's the plan for this talk. Let's start with star formation in a nutshell. I'll give you a moment to appreciate my choice of molecular cloud to illustrate this topic. Okay, hopefully someone laughed at that somewhere out there in cyberspace. The basic picture we have is that stars form out of the interstellar medium. Now, the interstellar medium is the low-density gas that fills the space between the stars. Low density here means an average of 1 atom per cubic centimeter. Now, most of the volume of the interstellar medium is filled with gas that is at a temperature of order 5 to 10,000 Kelvin and consists mostly of neutral hydrogen and helium atoms. And the reason it's warm is because it's kept hot by ultraviolet light. So UV light from stars is absorbed by dust grains that are mixed with the gas, which eject photoelectrons. Those bounce around and that heats up the gas, and that's why it's heated to temperatures of order 5 or 10,000 Kelvin. And it's constantly flowing through the galactic disk in response to the gravity of the stars and dark matter. Now, that stuff doesn't form stars. Most of it is way too hot for gravity to do anything interesting. Where things get interesting is in regions where a large amount of gas builds up, and as a result, it becomes opaque to that starlight. So the gas is mixed with interstellar dust. The dust is opaque to starlight. If you get a big enough column of it, the starlight can't get in. And in places where that happens, the temperature drops from about 10,000 Kelvin to about 10 Kelvin. The density rises to more than 100 per cubic centimeter. Now, just to put that in perspective, that's still better than the best vacuum chamber we know how to make on Earth, but it's 100 times denser than the average of the interstellar medium. And in these regions, the hydrogen atoms clump together to form hydrogen molecules, H2, and these regions are called giant molecular clouds. And we can observe these regions either via molecular line emission or via dust emission in the radio. And they typically have masses of order 10,000 to 1,000,000 times the mass of the sun and sizes of order 10 parsecs. And these are the regions where stars form. Now we can understand why from a simple physical argument. But before I get there, here's just a picture of how molecular clouds form in a galactic disk. All right, so this is a galactic disk or a simulation of a galactic disk. And what you're seeing is just the gas. And as the simulation runs, you'll see it clumps up and you have spiral arms forming, and there are these dense lumps of gas forming the spiral arms. And you will see as the movie ends that we have a lump of gas that might be a giant molecular cloud. So in the galactic context, this is where you find giant molecular clouds and what they look like. Now, just to show you that this isn't just a movie, this is sort of a realistic representation of what you might see in a galaxy. Here is an actually observed galaxy, and what you're seeing here in blue is giant molecular clouds as traced by CO emission, and what you're seeing in orange is sites of recent star formation as traced by ionized light, by H-alpha emission. All right, so this is showing you what a real galactic disk looks like. This is from Krekel et al. As part of the FANG survey. All right, so now that we know where you find molecular clouds in a disk, why do they form stars? Well, we can understand this very generally from a simple physical argument. Let's just consider an idealized spherical cloud of mass m, radius r, and density rho of order m over r cubed, with some sound speed in the gas Cs. And let's try and calculate under what conditions we expect it to be susceptible to gravitational collapse. Well, very simply, this is a contest between gravity and thermal pressure. So let's compare the gravitational energy, which must be of order gm squared over r, to the thermal energy, which must be of order mass times sound speed squared. And we expect collapse if the gravitational energy is larger. So you put those things together, and what you find is that there's a critical mass, which is of order the sound speed cubed divided by the square root of g cubed times rho, and we call this mass the Jeans mass. Now, if we plug in the typical density of at least 100 per cubic centimeter you find in a giant molecular cloud, and you put in the sound speed that you expect in gas at a temperature of 10 Kelvin, what you find is that this mass is of order 10 solar masses. It's much smaller than the 10 to the 4 to 10 to the 6 solar masses of the giant molecular cloud. So the conclusion you're driven towards is that thermal pressure is insufficient to hold up giant molecular clouds against gravity. They should start to collapse. So what happens when GMCs start to collapse? Well, since the Jeans mass decreases as the density rises, as long as the gas remains cold, all right, that's what you see here. The Jeans mass goes like sound speed cubed, but 1 over the square root of density. So if the density goes up, the Jeans mass goes down. Well, that means as the gas compresses, the Jeans mass gets smaller and smaller and smaller. So that means the gas tends to fragment into smaller and smaller pieces. There's a cascade of the gas breaking up into smaller and smaller pieces. But at some point, this has to stop. Now, exactly what mechanism is responsible for breaking the fragmentation cascade is still debated. It could be radiation or some other form of feedback from the stars that are forming within the gas. It could be something related to the statistics of the large-scale turbulence. It could be due to a transition between isothermal and adiabatic behavior in the collapsing gas. Exactly which mechanism is responsible is debated, but whatever mechanism that is, that determines the peak of the stellar IMF, that determines the characteristic mass of stars. Now, once that fragmentation cascade has ceased and you've started to form stars, you have gravitationally bound fragments with protostars at their centers, and those gravitationally bound fragments will begin to accrete. The accretion onto them occurs at a characteristic rate that's dictated by the sound speed. It's of order the sound speed cubed over g, and if you plug in the sound speed of about 0.2 kilometers a second that you expect in molecular hydrogen at a temperature of 10 Kelvin, you get of order 10 to the minus 5 solar masses per year. So that means that forming a star like the sun takes of order a few 100,000 years, a few times 10 to the 5 years, just because that's how long it takes to accrete its mass from a giant molecular cloud. So here's a movie of what this might look like. On the left, I'm showing you density, and on the right, I'm showing you temperature. And each of these dots you're seeing is a protostar that's forming. So we have turbulent gas, it begins to collapse, and we get a cluster of stars. I'll back up and play that again. Just so you can see, the gas is turbulent, it begins to collapse in its densest points first. The new stars begin to heat up the gas around them, and you wind up with a cluster of stars. So that's star formation in a nutshell. So what about disks? That's what most of the people at this meeting are probably interested in. Well, we can understand disk formation as follows. Let's idealize one of these collapsing clumps at the bottom of the fragmentation cascade as an idealized uniform sphere. And if we have a uniform sphere in solid body rotation, we can write down the ratio of rotational to gravitational potential energy. And that's this ratio beta here, which is given by the angular velocity squared divided by 4 pi g rho. That's the ratio of kinetic energy in rotation to potential energy. And it turns out that if the rotation comes from random turbulence, you can show both statistically and numerically that the typical value of this beta is of order a few percent. And if we further hypothesize that the gas collapses in a way that conserves angular momentum, what that means is that if a fluid element starts at some initial radius r0 and then conserves specific angular momentum as it falls in, it will circularize and go into a disk at a radius of order beta r0. So if we plug in some numbers, if we say we have a 1 solar mass clump of gas that's collapsing, and it's going to collapse in, say, 300,000 years. That gives us the initial density. Well, then the initial radius must be a few hundredths of a parsec, which means that you expect to circularize at a radius of order 100 AU. And indeed, that's about how big typical disks are observed to be. These images on the right here are observations of disks around class 0 systems, the youngest protostars, from the Van Dam survey by Tobin et al. And what you see is typical disk sizes are of order 100 AU, maybe a little smaller than that, probably due to magnetic effects, which mean you don't exactly conserve specific angular momentum. Specific angular momentum actually goes down a little as the gas collapses in due to magnetic braking. Okay, so we said it will take a few 100,000 years for most of the mass to fall onto the star. Now, during this phase, the accretion rate is quite high, and that probably drives the disk up to a relatively respectable mass, maybe a few tenths of the mass of the central star. What limits this mass is gravitational instability. If you try and make the disk too massive compared to the star it's orbiting, then the disk will become unstable in the formation of spiral arms, and that's what's shown in this simulation at the right from Crater et al., where you have a disk that's massive enough that it forms these spiral arms. And these spiral arms are very efficient at transporting mass inward. So you have these non-axisymmetric structures which drive non-axisymmetric torques. That probably drives accretion onto the star. Now that's the case only probably for the first couple 100,000 years while most of the mass is coming in. Once rapid accretion onto the star ceases, the disk will get much less massive, and then you won't have gravitational instability. All right, you'll typically have then a mass of order of percent rather than 10% of the central star, and accretion will continue at a much lower rate. Now, the exact mechanism that drives that accretion is unclear. It's almost certainly magnetic in origin, but whether it's magnetorotational instability or something like magnetocentrifugal winds is unclear at this point. What we do know from observations is that both disks and the accretion they produce persist for of order a few million years, and that's what's illustrated in this plot on the right. On the x-axis is age of different star clusters, and on the y-axis is percent of stars that show accretion. And what you can see is that there's this drop-off from most stars at ages of 1 to 2 million years to almost none by the time you get to 10 million years. So the e-folding time for this is a few million years. After that point, at least the inner parts of disks have disappeared. Exactly what mechanism does that is still debated. So now I've summarized all of star formation for you in 10 minutes. Let's talk about two hot new topics. And the first one I want to talk about is stellar clustering. So for people who don't work in star formation, you probably have heard the mantra a bunch of times: all stars form in clusters. So let's talk about that a little. Just to set the stage, the mean density of stars in the solar neighborhood is about 1 star per cubic parsec. And that's low enough that generally you don't worry about interactions between stars. They're just negligible. But stars can form at much higher density. If you go to the center of, for example, the Orion Nebula cluster, the density can be of order 10 to the 5 stars per cubic parsec. And even in regions that aren't quite that extreme, you see much higher densities. So this is illustrated in this plot from Pocrell et al. Showing the Mon R2 cloud, where you see in the center, this is 1 parsec, that's the scale bar, and there's a lot more than 1 star there. There's many tens. So the density is much more than 1 star per cubic parsec. Now, if the typical star is at such high densities when its disk is around, there are going to be possibly important effects from interactions between stars. For example, disks might get truncated either by dynamically or by radiation. You might get outer planets. I wrote plans. You might get outer planets ejected by dynamical interactions. You might get radioisotope pollution by supernovae. How big an effect is this? Well, depends on the density and whether you really think all stars form in clusters. So I mentioned a lot of people will say all stars form in clusters. Depends on what you mean by cluster. So the modern view is that star-forming clouds have a sort of hub and spoke structure where you have filaments of gas feeding mass inward to a central hub region like a conveyor belt. And that's shown in this plot from Mott et al., where you see these dark lanes, that's gas flowing inward to this central hub region. And this central hub region is what will go on to become a bound open cluster. Now here's the trick. We know that only about 10% of stars are in open clusters, even by an age of 10, 30 million years. What that means is that most stars form in the hub, not in the hub, but in the spokes. So yes, this is the part that'll go on to become a star cluster, but that's not where most of the stars are forming. Most of the stars are probably out here, and they're not forming an Orion Nebula cluster like densities. And we can see this directly with Gaia data. So here is a kinematic map of the Orion star forming region. Each of these dots you see is an individual star with an estimate for its age, and the blue and orange are illustrating kinematically disparate components. So this blue component is what's around the Orion Nebula cluster. The Orion Nebula cluster is this tiny little region here that's 1 parsec across. And the density of stars there is really big, 10 to the 4 to 10 to the 5 stars per cubic parsec. But that's only 10% of the stars. 90% of them are out here. And you know from the kinematics, they didn't come from the Orion Nebula cluster. These stars are not ejecta from in here. They were never in there, and they're never going to be in there. So most stars are forming at much lower densities than the really high ones you see in classical clusters. So do most stars form in clusters? Depends on what you mean by cluster, but for the purposes of interactions, I can say most stars don't form at densities of 10 to the 4 stars per cubic parsec. It's probably 2 to 3 orders of magnitude lower than that, which means that interactions are less important for most stars than a lot of people have previously thought. That's new topic number 1. Here's number 2, short-lived radioisotopes. So first of all, for those who didn't work on this, what are short-lived radioisotopes? And the answer is, they're isotopes with half-lives of order a million years, the daughter products of which have been found in primitive solar system objects. So examples are things like iron-60, aluminum-26, manganese-53. These are unstable isotopes that decay on a million-year timescale. All right, now, the interesting thing is, why would you find them in the young solar system? The more abundant of them are actually, in fact, important sources of heat in the early evolution of rocky planetary bodies. They may melt some bodies. Even when they don't melt things, they're important as chronometers. Now, some of these have no known origin sites other than the final stages of massive stellar evolution, which implies that the early solar system was exposed to massive stellar ejecta. This has been argued to be evidence that the sun formed in a massive cluster, or in a cluster that contained massive stars, in order for there to be supernovae around that could serve as the sources of short-lived radioisotopes. Let's look at this in the galactic context again. So here's a simulation done by Fujimoto et al. On the left side of the screen, I'm showing you the entire galactic disk, and on the right side, I'm just showing you a zoom in. In the upper left panel on both sets, I'm showing you all gas, and on the right panel, you're seeing the star formation rate. And in this simulation, we're following individual supernovae that inject iron-60 and aluminum-26. And so you can see the distributions of those. And you see these bubbles filled with iron-60 and aluminum-26 created when supernovae explode. Now, in this simulation, because star formation has followed itself consistently, we can just extract all of the stars forming at about 8 kiloparsecs from the sun, from the galactic center, about where the sun is, and ask, what's the distribution of iron-60 and aluminum-26 in these young stars? So here's the answer. In the plot on the right, I'm showing you the joint probability distribution of the iron-60 and aluminum-26 abundances. All right, so the colors are showing the probability density, and the green is showing measurements of primitive solar system objects. And what I want you to notice is that that green band slices across the full maximum of the probability distribution. In other words, the solar system actually has totally typical abundances. Now, this is interesting because those abundances are substantially higher than the mean throughout the galaxy. Why should most young stars have abundances higher than the mean in the galaxy? And the answer is because star formation is clustered in space and time. Even if the sun wasn't born in a cluster with a massive star, star formation is correlated in space and time, and so young stars preferentially form near the ejecta of a previous generation. So implication 1 here is that there's no strong constraint on the birth environment of the solar system. It's actually completely typical. Implication 2 is that heating from short-lived radioisotopes should affect most young planetary systems. The sun is not an oddball here. The amount of aluminum-26 we have in the solar system should actually be completely typical of all young planetary systems and should be incorporated into models as such. I have reached the end of my 20 minutes, and so I will say thank you for your attention. I hope you have found this talk informative, and I hope you enjoy this baby echidna for the end of my talk. Thanks very much.